Welcome to our lecture about synchronized measurement technology, or SMT. Today we will explain the concept of synchrophasors and we will have a look at how phasor measurement units work. Synchrophasor is a mathematical concept or tool that makes working with sinusoidal signals easier. It might not look like that at first glance, but it really is. Assume the signals we work with are really sinusoidal, with one fundamental frequency. That means there are no other frequencies or distortions or other shapes out there. In order to describe these signals, we can work with complicated formulas or do many measurements, samples in time. Or, and now comes the trick, we take just two values. The amplitude and the phase angle. Assuming the frequency is constant, we can represent the signal as a vector. We call this vector phasor. It has a certain length, it has a certain phase angle. And these are the two measurements, the two features that we need to know. Using complex numbers for that is the most convenient mathematical instrument to describe such signals. The original phasors would rotate with the fundamental frequency. For a European power system, that would be 50 Hertz. So if all phasors rotate, and we, as observers, would jump onto one of these phasors and rotate with it, we would get a different view. All phasors would stand still. They become simple vectors. Not phasors anymore, vectors. And we can use algebraic operations to calculate with them. And this is beautiful. Complicated signals can now be handled very easily. If one of the phasors does not have the fundamental frequency, but maybe 50.2 Hertz or 49.9 Hertz, then this phasor would not stand still in our reference frame. It would slowly spin. You see this here with the red dots that we sampled. And that would be the positioning of the corresponding phasor. This information is crucial in power engineering. When we measure sinusoidal signals in the grid, we want to see these phasors. They make the life of power engineers much easier. Luckily, there are devices to do exactly that. They are called phasor measurement units, PMUs. You see one of them here, a gray box, and such a PMU is part of a larger ecosystem called SMT, Synchronized Measurement Technology. The PMUs measure, maybe in a substation or on the bus bar, voltages, angles, frequencies, and so forth, and pack that into a measurement data stream. Here you see classical sample rates. Newer ones even have hundreds of samples per period, not just per second. And they send that data stream to the control room or to the application that needs it. In between is SMT infrastructure, such as phasor data concentrators, PDCs, fiber optic rings, and so forth. Important is a synchronization clock. The PMU needs an accurate time source to sample properly. Phasors cannot be measured. They are not a real thing. They are not an existing physical quantity. They are estimated using voltage signals and current signals that are measured. After sampling these signals with a proper time reference, you filter them, you convert them into digital numbers, and then you can estimate the frequency and the phasors. And then they are converted into symmetrical components and packed into a specialized PMU protocol. When we receive such PMU streams from all substations, we can see which phasors are aligned, what is the phase difference, and also if some phasors are moving. Besides the nifty concept of using phasors instead of physical sample snapshots, PMU have another advantage. Their much higher reporting rate. The blue curve here in this picture shows traditional SCADA measurements. Maybe every 5 seconds they make a sample and then you know what's out there. But in between, anything can happen. PMUs, however, measure just much more often. This gives you potentially important details. If you do a post-mortem analysis of an incident, or if you want to do sophisticated and fast controls, then you need these details. You need phasor measurement, not only individual samples every few seconds. The communication protocol of PMUs is a streaming protocol. You subscribe to certain data points, so you ask the PMU, please send me these and these and these data points. You turn the stream on with a special command, and then it starts. With another command, you can turn the stream off, and so forth. A rather simple protocol. The measurements, or more correctly, the estimations themselves are subject to a certain unavoidable error. The error stems from different sources. Maybe the time synchronization is not super correct. Maybe the sensor has a certain error range. Maybe the algorithm is not super correct. All that adds up somehow to a total vector error. And according to the PMU standard, a maximum error of 1 or 2% is allowed for static and dynamic cases. The picture shows the green estimated phasor within that blue 1% region. It satisfies the maximum total error vector. The red one is outside and thus not complying with the accuracy limits. So, you've seen the ecosystem of synchronized measurement technology. The central element here is the PMU, the phasor measurement unit, connected to communication infrastructure that transports the data. You can subscribe to a stream of data that contains estimated phasors of your sinusoidal measurement values in the substation. And they provide a high-resolution picture of the power system that you need for modern power system operations.